Chemistry, the Central Science, Chapter 8, Basic Concepts of Chemical Bonding, Lesson 1. So the octet rule tells us that atoms are going to lose, gain, or share electrons to get 8 valence electrons. So 8 electrons in their outermost shell in order to become stable. This is effectively the same thing as achieving a noble gas configuration. So elements become isoelectronic with a noble gas. That does not mean they become the noble gas. It just means that they have the same number of electrons. So for example, hydrogen has an electron, oxygen has 6 valence electrons. If we add in another hydrogen, we can see that oxygen has 2 lone electrons that are going to bond with those electrons that hydrogen has to form water. So hydrogen forms single bonds with oxygen and we get H2O. So in this instance, hydrogen has not achieved an octet because hydrogen only has a 1s orbital, so it can only share 1 electron to achieve a maximum of 2 electrons. However, oxygen has acquired an octet. So in ionic bonding, we have a transfer of electrons. We typically see that the metal is going to give up an electron or some number of electrons, and the nonmetal will accept those electrons. And then we're held together because something becomes positive and something becomes negative, right? Cations and anions come together and are attracted through electrostatic forces. So if we look at lithium, this shows the ionization of lithium to become a cation with a positive 1 charge, giving up its electron. Well, that electron can be accepted by fluorine that has 7. Then this is showing the electron affinity of a fluorine atom. So now we have a positive lithium ion and a negative fluorine ion, and we can form lithium fluoride. So fluorine has achieved an octet. Lithium, because it only starts out with 3 electrons, that it's going to have 2 now that it's given up 1. So looking at a lattice is a crystal lattice structure. So it's repeating units of your cations and anions, but we also see crystal lattice structures in other types of solids. Lattice energy is the energy that holds the ionic structure together. So once we have turned elements into a gaseous state, we have ionized them, they come together to form this solid. So it's the energy that is holding together every single one of these cations and anions. And when we look at this reaction here, we're seeing once again, sodium starts with 11 electrons. It gives up an electron. Now it has a noble gas configuration of neon to become positive. Chlorine will accept that electron. It will have the noble gas configuration of argon. And we can tell here that sodium has shrunk in size, right? Cations get smaller, anions get larger. So the chloride ion is bigger than the neutral atom. And then they come together because the positive attracts the negative, and we end up with sodium chloride. So we can look at calculating a lattice energy through the Born-Haber cycle, which is an application of Hess's law. So if we look at the left-hand side of the equation, we'll notice that this shows the standard enthalpy of formation reaction of forming sodium chloride, because we would get 1 mole of sodium chloride. So we can use that information. And then we look at the right-hand side and we say, how did we get to this positive sodium? How do we get to chloride? So we have to, first of all, sublimate sodium, right? So that's sodium solid to sodium gas. So that's the energy you have to put in. We have to break apart the bond in chlorine. And since we only need 1 chlorine atom to form sodium chloride, it would be half of that bond enthalpy. Then we have to ionize sodium. So that would be the first ionization energy to turn sodium into a cation. And then the electron affinity for chlorine is negative 349 kilojoules per mole. So that's what happens. The energy that is given off in chlorine accepts, excuse me, an electron. So then we effectively add up all of these values And you can calculate then what the lattice energy is. Excuse me. What the lattice energy is for a particular ionic compound. And when we're looking at lattice energies, two important factors that affect the magnitude of your lattice energy, and that's going to be the magnitude of the charge and the size of the atom. So you want to have smaller ions, right? They will be able to fit together more closely. And you want things that have a larger charge that would increase the amount of energy that's holding those cations and anions together. So now we're going to focus more on covalent bonding, which is why we're sharing electrons. So why should two atoms share electrons? Well, when you look at two things that have the same electronegativities, things that want electrons to the same extent, right? We don't have an instance where something wants to give one up to become more stable. They both want the electrons. So this is why atoms are going to share. So fluorine starts with 7 valence electrons. If they each share one, they can form a single bond, which forms the fluoride, or not fluoride, which forms fluorine, right? Fluorine as a gas, F2, diatomic fluorine. So each fluorine atom starts with 7, it ends up with 8, and as I said, it forms a single bond. So in looking at a Lewis structure, we can identify bonding pairs versus lone pairs. And so your lone pairs of electrons are the ones that are not participating in a bond. So each fluorine has 3 lone pairs of electrons. And there is a single bond between the fluorine atoms. So what happens is 2 hydrogen atoms approach each other, right? So as we get to this perfect distance, we notice that the potential energy drops significantly, which means that we're giving off energy. It becomes more stable for these hydrogen atoms to be bonded than what it is for them to be apart. So that's what this graph here is showing, that as we separate our hydrogen atoms, we get back to a potential energy of 0. If we get them too close, of course, then they would start to repel each other because the nuclei are, positively charged. So we'd end up with a major repulsion, but there's this perfect distance with which atoms can overlap and share their electrons to become stable. So some examples of Lewis structures, we've seen things with single bonds like in water and in the element fluorine, right? Diatomic molecule. So carbon dioxide forms a double bond, which means that carbon is sharing 2 pairs of electrons with each oxygen atom here. And we see then that oxygen ends up with 8 electrons because it has 2 lone pairs and 2 bonded pairs. And carbon has 8 electrons as well because it has formed 4 bonds. And we see this as 2 double bonds. So everybody has their 8 electrons and is happy. Remember, a single line is representing a pair of electrons, just like 2 dots represents a pair of electrons. It's just a matter of whether they belong to a single atom or they're between 2 atoms. Diatomic nitrogen, right, elemental nitrogen, forms a triple bond. So each nitrogen brings 5 valence electrons. It's going to share 3 electrons, respectively, each, and we form a triple bond, so that each nitrogen then ends up with 8 electrons. So in forming a triple bond, we have 6 total electrons involved in that. So the bond length is looking at what is the distance between these 2 atoms that form a bond, right? What is their distance away from each other? That is what a bond length is. And we can look at this table and see that single bonds are going to be longer than double bonds, which would be longer than triple bonds. So the more electrons you're sharing, the tighter you are with that atom that you're sharing them with. So if we look at carbon to oxygen, we see a single bond is 143 picometers, the double bond is 121, and the triple bond is 113. So as we increase the number of bonds between 2 atoms, we decrease the bond length. So, in looking at electronegativity differences and how we would form a polar covalent bond. So, a dipole moment is just simply looking at the fact that there is a separation of charges. So, this is showing an electrostatic potential map of hydrofluoric acid. And the positive side of this is shown in blue. So, electron pour, which means that fluorine is pulling hydrogen's electron towards it within the bond. So fluorine is holding the electron closer to it. On the right-hand side here, we see a little pink symbol. And the positive side is showing where it's positive, and the arrow is pointing to the direction that it is negative. So this is called a dipole moment. So fluorine is electron rich, hydrogen is electron poor, and we can represent this by saying sigma positive or sigma negative. So as I had mentioned, this comes from the fact that we define a term called electronegativity, which is how much an atom will pull on electrons in a bond. So this is different than electron affinity. Electron affinity is measurable, where chlorine is the highest. Electronegativity is simply looking at all these different electrostatic potential maps and seeing where do the electrons sit most of the time. Well, if you look at all these compounds that have fluorine in it, it was shown that the electrons are closer to fluorine. So fluorine was assigned a value of 4. And then they look at all the ones with chlorine and all the ones with oxygen, seeing where the electrons sit. And so values were assigned as electronegativities to show, hey, if these atoms are in a bond, the electrons are not evenly shared per se. Where are they closer? Which atom are they closer to? It's like a tug of war on electrons in a bond. Right? We just remind ourselves that electron affinity has an energy of kilojoules per mole associated with it. Electronegativity has no units. It is an arbitrary scale that we use. I shouldn't say arbitrary, but it's a scale that was derived by Linus Pauling. So electronegativity is the highest for fluorine, but the electron affinity is highest for chlorine. So in your book and in this table here, we see electronegativities. And in the next slide, we'll talk about the sliding scale between being an ionic compound versus being a truly nonpolar covalent, right? The difference between, did we completely transfer our electrons or are we completely sharing our electrons? It is a sliding scale. If you want to calculate bond polarity, all you do is look at the atoms in a particular bond and you subtract the values. So if I wanted to know what is the electronegativity difference between aluminum and phosphorus, right, which would form what we would typically consider an ionic compound, I subtract those two. So phosphorus is 2.1 minus aluminum, which is 1.5, gives me a difference of 0.6. So I can do this for any two atoms that are connected to each other. As we have been looking at trends in Chapter 7, we can look at the trend here with electronegativities, and we show that as you go from bottom to top and left to right, we increase our electronegativity. So the closer you are to fluorine, the more likely you are to pull on electrons in a bond, which hopefully makes sense because we've talked a lot about how metals want to give up their electrons. So it wouldn't make sense if the electrons were closer to the metals, right? Non-metals want the electrons, metals want to give them away. Then we have a scale, and the scales vary, but if you're less than 0.5, we consider that to be completely nonpolar. If you're between 0.5 and 2, you're polar, covalent, so that means you have a dipole moment, and if the electronegativity difference is greater than 2, we consider that to be an ionic bond. And so once again, you're just looking at those electronegativity differences, and we can then calculate what we would call percent ionic character. And as I said earlier, it's a sliding scale. So down at the bottom of this graph, we see chlorine, right? Cl2. Chlorine and chlorine bonded together would be completely nonpolar because it's the same electronegativity, so they cancel each other out. Then we see this mixture of some hydrogen in there and then some halogens bonding to each other. And because the electronegativity differences are so close to each other, we would consider those to basically be effectively nonpolar. Once you get into a hydrogen bonding like hydroiodic, hydrobromic, and hydrochloric acid, we start to see some polarity. And then as we go up the scale, we see that when we have metals bonded to nonmetals, we get closer and closer to being ionic, with lithium fluoride having a really, really large difference in electronegativity. So once again, there's this, we've talked before, ionic compounds are metal and nonmetal, and covalent compounds are two nonmetals. Well, it is a sliding scale between whether you are ionic, whether you are polar, covalent, or whether you are nonpolar, right? And that idea of being polar just means that the electron hasn't completely been transferred, but we're not sharing our electrons equally. So in this last slide, I just wanted to just compare ionic compounds versus covalent molecules, just to give a brief overview, or a summary, I guess, between the two. So ionic compounds are solid at room temperature, whereas covalent compounds can be solids, liquids, or gases. The melting points of ionic compounds are going to be much higher than those comparatively to covalent compounds, right? 801 degrees Celsius versus -23. Heats of fusion for ionic compounds are higher. Boiling points are higher. Heats of vaporization, because you have to actually disrupt that lattice energy, right? You have to break apart every single one of those cations and anions to truly separate things back into their elements, whereas in molecules, you just have to break apart the covalent bonds. Densities of ionic compounds tend to be higher. Solubility in water varies, but typically your ionic compounds will be soluble. We looked at solubility rules, but typically we see pretty good solubility in water, where molecular compounds sometimes are, maybe not so much. And then as far as electrical conductivity goes, when you dissolve an ionic compound into water, it's going to conduct electricity really well. As a solid, it won't, but if you melt it and you have molten sodium chloride, it also becomes a good conductor of electricity, whereas your covalent compounds have very poor electrical conductivity because there's no ions there to carry an electrical current.